Hello, hello. This is our second session about reinforcement learning. And this time we are going to talk about food, which means we all eat and we like better food. And today we will hear from Michal Yushchuk what reinforcement learning can help us with growing our plants in the greenhouses. So, Michal, the stage is yours.
Yeah, thank you for the introduction. So, my name is Michael, and I'm data science lead in Quantum Company. And today I'll tell you a little bit about our research projects on how to grow plants in autonomous greenhouse. So we will talk a little bit on what is reinforcement learning for those who doesn't really familiar with it. Also, we talk a little bit about how autonomous growing looks like nowadays, what is greenhouse and how it might be operated, a little bit on real algorithms and working process, also a little bit on results and our future developments, maybe also interesting. So introduction about me. So I am data science department lead in Quantum, so leading a team of 15 data scientists, also leading the R&D department in our company. And this project is a part of our R&D. Also working with different Ukrainian universities, and now we're starting to work with Polish universities, also with Israel universities. During this collaboration, we get sometimes some scientific papers, maybe patents or something really interesting. So it was brief about me and who I am. Now let's go straight to reinforcement learning. So as you may know, as a data scientist on a daily basis, you used to work with supervised learning or unsupervised learning. Yeah. So when you have some data set and maybe some labels for this data set, and you could have some features from it and train some models. If you have labels, it could be supervised, classification, regression, and other tasks, or unsupervised, something like clustering, just to get points. But remember that you should have some data, you can have some features, and all your work is around this kind of framework. But reinforcement learning gives us a little bit different view on actually learning problem. Yeah, so when you have some environment, it could be world, it could be game, it could be something, and you have some agent or policy, and this agent could do some actions on this actually environment and get some observable states and reward for each action. Yeah, so you don't have any kind of pre-collected data, you just run your agent and then tries to figure out how to live in this tough world or environment. And main thing here, of course, it's set of actions which you decide like an engineer, and of course state what agent observes during the process of interaction. And reward, it's also designed by people, by human, how agent progress and how agent understands that doing something really correct. So there is no like labels like 0 or 1. It's all different. So yeah, now this really complicated slide with taxonomy of all reinforcement learning algorithms and models. So I will not talk about any algorithm, just brief, introduction of what might happen and what actually researchers developed during last 50 years. Yeah, so I can start from root. So reinforcement learning is divided by Markov decision process and bandits. So bandits is something simple based on sampling strategies. Markov decision process is, as you may see, tree grows from here a lot. So it's something really used in state-of-the-art models. Then it could be model-based or model-free. Model-based, it means that you have some physical mathematical model which describes your environment, and you actually can exploit it while you're learning your actually agent, because agent might understand some rules, which is much easier to learn and to get some good rewards when it knows some physics of how system works. For example, chess or Go game, it's also based on model-based, because there is a model on how chess moves around the field, or how you can do some moves in Go. But main majority of algorithms is model-free, because it's really hard to create some really good physical mathematical model of any environment. Of course, if it's not a simple game like chess. And here we have value-based and policy-based methods. So as I already said, so there is kind of policy, and agent, it is the same mainly. So there is some function that given state returns you some action to do on the next step, and you just iterate. In value-based methods, researchers also added another function which do assessment of quality of your current state. So given state and action gives you value. So it's something and defines the quality of your current step. Yeah, and this method could be on policy or off policy. So on policy, it's not really sample efficient, because you always use your latest weights. So you did the gradient backpropagation if you're talking about deep learning, and you use this weights updated to plan the next action. Off policy, you can have some experience replay buffer or memory buffer when you store some previous actions, and you can randomly pull this action during your training process. So of course it's not so stable as on policy, but this strategy gives you ability to avoid some local minimas, and you don't need so much interactions with the environment, because you could do some actions, you can store it to the buffer, and you can get something from memory buffer and get something from environment, update the buffer in some smart ways. So it's more kind of sample efficient, and if you have some boundaries on interaction with your simulation or real world, so it might be for you. And of course, it grows further for some decans, and then some dual indicans, soft actor critic, and now it merges all together like in above range. So I will not talk about each model deeply. We will talk about one which we actually applied. Yeah, so it's kind of brief. Now let's talk a little bit about its application in the real world. So where it is applied in autonomous systems, like autonomous greenhouses, for example, or maybe in some autonomous driving. But in autonomous driving, I didn't so really prove that it is actually implemented. In something called Industry 4.0, so for some robots, you might want to learn some policies on changing environment, changing world. I will show you some example. And I believe the kind of best way to apply these models nowadays is some recommendation engines. So when you give some recommendations to user on your website and you want to increase the click rate on recommended items. So let's go briefly here. So I just looked for real production application and found this robot. So researchers made actually robot to move the bags with coins from the cart to the table. And just so this kind of robotic hands should take the bag, take it out and put to the table. It kind of looks like simple task, but of course it's not so simple, because size of bags might change, the amount of coins inside might change, and also grip force should be also changed, depends on how many coins and how robot arm took this. And it's not really simple kind of problem to solve, and researchers used the soft actor critic algorithm and also proximal policy optimization to train some model So it, as you can see here, they does instance segmentation. Then they create some kind of shape model and give features to the model as input. And policy gives the prediction on how to grip, how to put this, where to put actually the force and grip this index. So as I saw, as they state, they already sell these robots with reinforcement learning side, which is pretty exciting. Second one is application of recommendation engines. So it's multi-armed bandits. So bandits, its algorithm main key here is kind of sampling. So you do the some smart sampling and you remember which actions lead you to good reward in current kind of state. So you just took action. If it gives you reward, you add +1 to this kind of level in this game. If not, it's 0, and you iterate and you build some kind of probability function on what level you should choose in some action. And these guys from this startup, so they used these bandits on top of gradient boosting to boost up the recommendation engine. So here is the link. This article, there is really many interesting details about this. And of course, third one, it's autonomous growing, on which we kind of have some hands-on experience lately. So what it is and what it's about. So right now in the world, our goal is to, beat up the hunger. And for example, in Netherlands, there is a lot of universities and organizations. They put some effort to automate some processes in farming, in greenhouses as well as in real farming, in big mountains and fields. So what we focused on, it's greenhouses and how to grow some crop. In our case, it was lettuce in the greenhouse. So what we want to have actually is it's minimal human intervention. It might be the labor cost and also cost of growers, actually the human agronomist, so who know how to grow. And of course, we want to get maximal profit. So we want to have a good quality product and want to sell it for a high price and use as much as less electricity, gas, and all other expenses. And this means we should use optimal growing strategy. So for example, in some cases, when gas price is really high, farmer might want to decrease the growing rate and spend more money on rent of greenhouses, but still save money on gas or some resource. So the system should be kind of flexible to some adjustment from the actual customer, I would say. So where we get such an ability? So last year, Wageningen University in Netherlands conducted the third edition of Autonomous Greenhouse Challenge, and we competed in it, and in team with our Chinese and Netherlands friends. So they was more like horticulture experts, so who know how to grow lettuce, and we was more like from data science and from algorithmic part development of the process. So it's kind of big competition. There was 17 teams from leading research universities from Netherlands, USA, Korea, Russia, and other countries. So there was 3 rounds. First one, I will not talk about it. Second round was hackathon. It was 24-hour hackathon, so we was kind of tight on time. And third round, it's industrial greenhouses. They give us to us, and we should grow a real lettuce in real greenhouse without human intervention at all. So today I will tell you about second round, about hackathon and lettuce simulation. Okay, so what is simulation? So organizers kindly provided us with a good simulation. So there is a software called CASPRO, and it's actually simulate the greenhouse with all the sensors, with all the controls, and you can put their mathematical model of your crop. So organizers created this simulation, created the mathematical model of crop, and gave it to us. So what we have as a sensing is a state of agent, I would say. So we have humidity sensor, temperature, wind speed outside, solar radiation forecast and current state, and CO2 level inside the greenhouse, and weight measurement each day. So simulator gave us the weight of our lettuce. And our goal is just to grow to 150 gram lettuce with cheapest cost. Yeah, so 250 grams is for each head we have like 55 cents. So then calculated to the profit, we subtract the expenses and we get the result. Yeah, so it's kind of our sensing things. So now what we want to control. We could control the heat pipe temperature, ventilation, so it's how the angle of windows, screen control, so it's maybe we want to do shading or energy saving. There was a different screens which might be applied to the greenhouse. Plant spacing, so it's also important thing because lettuce, if it grows too tightly, it might fall apart. CO2, for me it was really big news that growers in greenhouse apply CO2 from tanks. Yeah, so and that's why ecologists in the whole world say that the greenhouse is not really ecological stuff. Yeah, so mainly we control the amount of CO2 provided to the plants. So it's kind of food for plant, right? And light control, it's how much food plant could eat. Yeah, so more light you have. So if you turn on the lamps, the more CO2 you need, that increase growth of plants. And of course, harvest date. Yeah, so if you will not stop our growing, it will grow eternally. Yeah, and it was actually the easiest one because we could check the weight daily, and if it is enough, 250 grams, so we can harvest it. So it's the simplest one. Yeah, so I mentioned that in our team we had an expert who actually know a lot about horticulture and how to grow. So we asked our expert to put some boundary conditions to our agent. So for example, if temperature is lower than 5 degrees, it's not reasonable to grow anything. Or if you put your screen with shading on whole the day and you will not get any sun, so plants will not grow. Or if the amount of humidity will be higher than 90% and temperature will be higher than 30 degrees, there will be some diseases on our crop. So they kind of provided us boundary conditions, so temperature should be from 5 to 25, have humidity in such range, number of lights per day in such range, so there was a lot of boundaries for our agent to speed up the learning process. And then we provided these to our agent, and it started to work with simulation. So we were able to make requests and get back the results. So after the simulation process is finished, agent gets some convergence. We get some plots of weight, temperature, all the kind of parameters we set up and what we get as output. And then we go back to experts and say, okay, so this is the result. Maybe you can tune something. And we tuned. So there was an expert from horticulture perspective and also VR, because our goal was to define good reward function for it, but I will talk about it on next slide. Yeah, so the procedure like this. So we wanted to minimize kind of agent exploration thing, just reasonable ones. Now, when we understand our process, let's a little bit talk about algorithms. So what we can use here at all? So we can use some feature-based machine learning. So for this, we should trigger a lot of different weather conditions and different settings to get some training data. So we think about it like 5 minutes before we start the hackathon, and decided that it will be not really possible to get fast such a data set and get all that from the data. So we just moved it out. Second one was genetic algorithms. It's also a good choice comparing to reinforcement learning for some particular tasks. But in our case, we saw that, okay, so growing cycle will be like 30 days. And we want to put for each hour 10 parameters to control. So it's 30 multiplied by 24 and by 10. So it's just a lot of choice for each kind of genetic algorithm species. So we just could run it and never get to the convergence. So we decided, okay, let's leave it aside and let's apply some reinforcement learning because we waited just a chance to apply it somewhere. So our choice, of course, is reinforcement learning here. Now let's talk a little bit more on algorithm and our reward function. So, of course, we started with analyzing some literature about this. We found that soft actor critic actually applied to similar control problems like data center ventilation issue or in greenhouse, also growing optimization. So we found the implementation on GitHub and started to explore it and use it. From our experts and economy analysis of the simulation in greenhouse, we saw that it will be really great to grow crops fast. So it's kind of, if you grow crop during 20 days, not 60, you save 40 days of rent of greenhouse and some costs like land cost and other, kind of fixed costs, which gets more during the growing each day. Yeah, so our strategy was to grow fast. Let's a little bit talk about soft actor critic algorithm. So it is kind of proximal, so something intermediate between on-policy and off-policy algorithms. So it's said to be off-policy. So we had there this experience buffer. This is the first one. Why it is soft? Because it's cross-entropy regularized. So there is an additional term when we calculate loss function with reward. There is entropy, and actually entropy gives us ability to adjust the exploration to exploitation rate. Yeah, so in reinforcement learning, if we always choose the best possible option to act in next stage, we might end up not in really good place because agent didn't saw all the opportunities like this, and we have some exploration rate. And this kind of more entropy we have, more exploration we run. So, and this parameter also is tuned during the training. And what we wanted actually is to iterate really fast because we need apply some boundary conditions, check the reward function, run some iterations, then get back, understand what we're doing wrong, how simulators act, and I want to mention that we had only 24 hours, so we didn't have a lot of time to just to run some multi-GPU machines for days and hours finding the best option. So this was kind of really tough restriction. So soft actor critic, because it's off policy, it's sample efficient, so we kind of have some experience replay buffer and we can use it. This entropy gives its ability to converge pretty fast. So on my laptop with i5 without any GPUs, I was able to run and one experiment with 100 growing iterations. So growing, I mean from the seed to the harvest during the 20 minutes. So kind of each 20 minutes we get the plots, we can check, analyze, and tune. So also you can see here is the weights plot. Yeah, so how weight of lettuce is changed during the time. You can see it is kind of geometrical progression, so it increased during the time. And now what is crucial in any reinforcement learning algorithm is reward function. I even saw the papers that guys just say, okay, we designed a new reward function for this particular task, and we publish it as new scientific research because it's really something crucial here. I'll reward a lot of stakes. Yeah, so our reward was like profit, it's P, minus cost. What is profit in our understanding? So it's change of the weights during the one day. Yeah, so today weight minus yesterday multiplied by weights for 1 gram and number of days. So this one will grow daily. Of course, if weight doesn't change, it doesn't grow, so we don't really get profit. And this perfectly matches with our idea to grow fast. And also the cost. The cost simulator gave us each day, so it's okay. And we also add 5% of cost daily. So it's also kind of, you'll have some kind of geometrical progression like this. So it's also connected to idea to grow fast. And if our lettuce doesn't grow at all, so the weight changes, well, so here I have coded 0.5, but in the real challenge, we put like for each week number, because it changed differently. So, and if it doesn't grow, we just put reward minus 50. So the agent doing something completely wrong in this action. Okay, so in this kind of final reward function after 24 hours hackathon. Okay, so we are here. So we have algorithm, we iterate, and what is the results? Yeah, so you might think that there was 17 teams, all use reinforcement learning or any another nice algorithms. So let's just check. So our team Vegemite here. So we took the third place among 17 teams. And for me, it was really surprised that our algorithm and actually this reinforcement learning could work, because as a person who does a lot of projects in data science, I saw that it is all just, could solve some toy problems like games. I also have some kind of toy problem, but it's more connected to real life. Yeah, so it was kind of a surprise for us that we was able to get this third place. So as I remember, so you can see here a balance. It's actually the result, euro per square meter. So we grew really fast, so in 22 days. And here you can see some stats about expenses, what we spent, how much CO2 we spent, and all of the things. What quality loss we have for the too tight plant growing, what fixed cost, and what gains. Yeah, so I was able to grow for 14 and spend like some of these ones. Yeah, so as we talked afterwards with other teams, so first team they used feature-based machine learning, so they somehow exploited the simulator and found that in 70 days, 70 it's really a lot, so the usual growing cycle from our expert was like from 26 days to 36 days. So it's really a lot. But okay, so they don't use any lights and they use some feature-based machine learning without reinforcement. So team on second place also used reinforcement learning, but another algorithm. for Series 3. And these teams, among the latest, also used some reinforcement. Okay, so what is the conclusion here? Might be, so we was able to run reinforcement learning in pretty short time period and get really good results, which is great. And now I have some beliefs that it could work. So it hacked the simulator actually. Afterwards, when we tried to apply our algorithm on real greenhouse, of course we faced the issue that simulation is not reality. Yeah, and actually the simulator was kind of overfitted for some values for some growing cycle, growing strategy of the kind of reference grower. And if you try to apply another different strategy, it fails. But in reality, you could have really much bigger choice. So you have these boundaries still, but you could explore much more. And this is a real issue of reinforcement learning application. So if you have good results in simulator, it doesn't mean you will go boot in production in real compartment. And of course, we want to focus now on product development because during the challenge, we saw a lot of traction from the investment point of view, from the growers point of view, because on daily basis, there is like, you can see in the background, a lot of greenhouses building up, and you need the people who, and the growers who actually know how to grow. And this is a problem because it's kind of, you should get some high master degree on the growing some plants. And it's hard to find such people in needed amount, I would say. So some solution or some product to scale up one grower to many greenhouses will be really perfect fit for the next, I believe, 2 years to get some investments and develop the product. And I believe this will be the end of my presentation. So thank you for having me and for attention. I will be really glad to answer your questions if you have some. Yeah, thank you.
Okay, thank you very much, Mihail. So now we know that we can make money from growing lettuce automatically with no human intervention, or nearly no human intervention. And there are a few questions from the public, and I want to go very quickly through them because we are a little bit late. Okay, and the question, it's actually a set of questions. How did you evaluate your algorithm? Did you check that the resulting growth would be faster or slower? Experimentally, how was it compared during the contest? Or maybe the growth was simulated by field specialists?
Yeah, so the mathematical model inside the simulator of growing, so this one curve here, it depended on some parameters of growth, about amount of light, temperature, and stuff like this. And of course, the simulator gives us the result. So we kind of grow daily, apply some parameters, then we get to 150 grams and we stop. So, and we see how many days we did the actually growing cycle.
Mm-hmm. Okay. Thank you very much. And thank you very much for the presentation. It was very interesting. I must say to my friends who are farmers that there is future with, machine learning or reinforcement learning in front of them.
Okay.
So, and thanks very much for attending the session. And you can evaluate it in the bottom left corner. You have those 5 stars, and you know what to press. And thanks, Mel. See you on the next session. Cheers.
Yeah.
Bye.
Thank you.